Please allow me to introduce Ehsan Adeli from Stanford University of United States. Dr. Ehsan Adeli is an assistant professor at the Stanford University Department of Psychiatry and Behavioral Sciences and is affiliated with the Computer Science Department. His research interests include computational neuroscience, computer vision, machine learning, and healthcare. Dr. Adeli is an executive co-director of Stanford AGILE Consortium, which aims to develop methods to diagnose and treat frailty. He is an associated editor of two journals in the field, IEEE Journal of Biomedical and Health Informatics and the Journal of Ambient Intelligence and Smart Environments. He is a senior member of IEEE and has served as area chair for several conferences over the past 3 to 4 years. His speech title is Dealing with Confounders and Bias in Medical Studies in the Age of Deep Learning. Dr. Adeli, please share your screen. Wait a minute. Okay.
Thank you. Can you hear me?
Yes.
Great. And yes, and I now can share my screen. I'm going to share, and you should be seeing my full screen.
Yes.
All right. Great. Hello, everybody. Talking to you from the sunny California. I'm thrilled to be here and deliver this keynote talk at BigHeart 2022. Today, I'm going to talk about dealing with confounders and bias in medical studies in the age of deep learning, a topic that is probably of a great importance. And I noticed that the last question from the previous keynote talk could be relatively or rather answered with some of the methods that I'm presenting in this talk. Okay, let me first define confounders. A confounder is a variable that influences both the outcome or the output and the exposure or the input in a study, causing a spurious or distorted association when building a model to predict the outcome from the inputs. If the confounders are not properly controlled for, we may obtain inconclusive results. For example, when we predict the diagnosis from the brain images, age can confound the study because we know that at different ages, human brain looks differently, and hence brain image is largely affected by age. On the other hand, the disease diagnosis could be a function of age as well. For example, this diagram shows the distribution of Alzheimer's disease patients in each age bucket. And as another example, this one shows distribution of HIV diagnosis as a function of age. Furthermore, data sets could also themselves be biased by, for example, the variable age, having different age distributions in the cohorts or groups under the study. If we do not appropriately control for these confounding effects, when building machine learning or deep learning models, we may be learning the effect of age instead of the actual disease. It's not just age. All other demographic variables, sex, race, acquisition site, and so on, as well as even treatment procedures, medication usage, or disease comorbidities can all induce sorts of confounding effects. The literature offers several traditional methods, one of which is data stratification. In this method, we stratify or group the participants in buckets with several values of the confounding variable, for example, different age ranges. And then we build different models for each of these groups. This is an interesting method, but it limits the number of samples each model is trained on, which is not of great interest when aiming to train large-scale models. Another method is matching. And this method, for each class of the outcome, outcome diagnosis variable, we select a subset of the participants such that the groups are matched with respect to the confounding variable. Although this method helps building less confounded models, it cannot guarantee perfect independence from the confounding variables, plus it discards some samples that could otherwise be used for model training. One of the most relevant methods is to statistically remove the confounding effect from the input features. To this end, we replace the images with some features such as volumetric ROI measurements. We then residualize the confounding effect from the features and replace them with new values. To do so, we build a simple general linear model, or GLM, based between the confounding variable, and one specific measurement, each specific measurement. The new feature value will be the previous value minus the amount that is explained by the confounder. In this case, the dotted lines indicate the new values. This is a widely used method in statistics, but requires a pre-computed, handcrafted feature values. When it comes to end-to-end learning, the residualization methods, the method does not apply anymore. And hence, controlling for the confounding variable is not a trivial task. To recap, end-to-end learning involves a subnetwork that extracts features, let's call the features F, and then classifies or predicts the output Y. After training this model, we can use different methods for interpreting the learned models. But the question is how should we account for confounders? In this space, we have published several works on interpretation of the results in the presence of confounders, learning features invariant or independent from confounding effects, and finally, building models in truly end-to-end fashion, which I'm going to talk about. Let's start with the first one, interpretation. Back to our end-to-end learning setting. We can build models and then build interpretations out of them by looking at what the model has learned. There are several methods in this space. In one of the works to make interpretation of an end-to-end model that is previously learned, it's trained. We just want to interpret them. And see how the learned model was affected by the confounders. We analyze each learned feature in correspondence with the prediction score SI that is generated by the model. We perform the exact same traditional linear model using the feature, the outcome variable, and the confounding variable, which is shown by variable Z in this formulation. we build the general linear model, or the GLM again, and perform a statistical significance test to see if the feature Fj is confounded or not, generating a binary mask, as you see in the slide, and therefore a mask vector for all of the features. We plug this mask in the model within a dummy layer and perform a partial backpropagation method that we proposed in this paper, and generate confounder-free saliency maps for each input image. Basically, through this process, we mask any feature that is confounded and only keep those that are unconfounded. We tested this algorithm for the task of identifying sex differences from MR images of children. We ran this on the ABCD data set, which we actually ran a challenge on in MICAI 2019 as well. In this study, pubertal development scale, or PDS, was significantly different between boys and girls, as you can see in this table. For the boys and girls in the age range of 9 to 10 years old, and hence we counted that as a confounder. Our model was able to generate a first saliency map that was showing the differences between boys and girls in the brain. But this is the initial bitmap, and our model was able to remove the effect of the confounder the same way that I presented, which shows this bitmap. The difference between these two is mainly in the cerebral region, and this, which we identified to be the effect of the PDS confounder in the results. We further, from the heat maps, extracted the specific regions. Our algorithm found a difference between boys and girls. Some of these regions had significant differences in their volume as well, which are shown here in this table. Now that we saw how we can interpret a learned model, let's see how we can learn features that are independent from or invariant with respect to the confounder. To this end, we trained an adversarial model that learned to extract features F based on which Y is predicted, while invariant to confounding variable C using an adversarial component, which we called it CP. So we published this idea first in this computer vision conference and ran it on several different vision tasks, in which we designed a batch level loss function based on correlation coefficient between the actual and the predicted bias protected variables, as you see here. And the classifier used a simple regular cross entropy loss. Therefore, the overall objective of the model was defined as a mean max game between the CP and C subnetworks, similar to GANs, how GANs are trained, with a trade of hyperparameter lambda. Our method guaranteed mean statistical independence between the learned features and the protected variables using the proposed vanished correlation scheme, as I explained here. Refer to the paper for the theoretical analysis and more details that included. Okay. However, in medical studies, we have another big challenge. To understand this, let's look at this example. We have two classes of data, disease and control, as you can see here. When you want to model the effect of, say, age. The challenge is that, as you can see in this diagram too, there is already an intrinsic correlation between the confounder and the disease label, or the Y outcome. Therefore, we can simultaneously predict Y from the features F while the features are invariant to the confounder C. So this is a huge challenge, and therefore, what we did was, to solve this problem, we need to enforce the invariance condition only based on one of the cohorts, for which we select the control group in this example. As a result, we designed a switch row, as you can see in the slide, which makes the adversarial head CP only backpropagates the loss for the control group. This means it is Y conditioned. Doing so, we show in the paper that F will become mean independent from the confounder C. We solved this problem using the same min-max adversarial training framework, and only enforce the switch row in the second term, as you can see. We tested the model on our lab HIV data, which has age as a significant confounder. As you see, it's significantly different in the groups here. We showed improved accuracy compared to when the model was not controlling for the confounder, meaning that this independent feature learning not only removed the bias from the confounder age, but it was able to regularize the model to generalize better to unseen testing data as well. This was further verified by looking at matched age buckets to see how our method compared to a regular convolutional neural network worked, as well as when we specifically evaluate on young and old subgroups. Let's look at some visualizations. The visualization of the learned features by the models in the middle, you see, shows that our model's feature space is not biased by age, while the regular Convex feature space clearly shows a pattern with respect to age. The plot on the left shows how our model was able to generate correct predictions for both young and old cohorts, while the ConvNet was biased by age. And finally, on the right, we also see the saliency maps, which again show removal of the ventricle areas when our CFNet model is used. We know that the ventricle areas are highly associated with aging and aging processes, and the interpretation of the results here also shows that our model was able to remove those effects from the model training. All right, finally, we proposed models to use in any end-to-end learning framework for controlling the confounding effects. For end-to-end training of the models, we know that batch normalization and its variants have been extremely successful in improving the training of machine learning models by standardizing features within a batch. However, they do not correct the distribution of the features with respect to external variables, referred to as, in this work, we call them metadata, but they could be same as the confounders or any information from the data that can be used to correct the feature values. So these variables could create bias or confounding effects, and we try to control for them in this work. As we discussed before, prior methods which remove the impact of the protected variables include regression analysis techniques with GLMs, general linear models. This is a common technique which builds a linear model between features and metadata, as I explained earlier, and then takes the residual between the features and the linear model as the new input. However, we know that this technique only works for high-level and hand-computed features to build the GLM, not for pixel level or continuous input required by deep learning model, end-to-end models. Additionally, we mentioned that batch norm and its variance cannot account for multiple or bias distribution that I mentioned. So our method is, so this is why in a recent work, we proposed a simple layer that works end-to-end on pixel or voxel level data and corrects the distribution shift from metadata. MDN places the regression analysis technique within a network using the key idea that intermediate features of a network may be high-level features. To this end, in a network, an input layer L with features F is the input to the MDN operation, which projects F onto the metadata space and then outputs the residual to the next layer L+1. So basically bringing in that statistical operation right into the normalization, to a normalization layer in the network. We tested the algorithm on a data set from 3 different sites with multiple output labels forming 4 different classes. The site variable was considered as the confounder that we wanted to control for. Basically, this procedure aims to remove the effect of site differences and, in other words, harmonize the data. Our results show that MDN can obtain better accuracy results while removing the correlation of the learned features to the site. This was also verified in the visualization of feature embedding space, where we see that the method with MDN space does not show any patterns of bias with respect to the 3 sites, while the other methods, including batch normalization, as you can see, there is a specific, very clear pattern of differences between the 3 sites in this study. We did see the solution to MDN, but basically, what MDN was doing, using the metadata variable and input features from all of the samples in the batch, MDN computed a vector beta using the closed form solution of least squares, as we discussed, and the metadata variable and beta are then used to calculate residual R given to the next layer of the network. The network is trained using the overall prediction loss. As can be seen here, the network was a batch level operation. This network had a batch level operation. We had to calculate beta in each of the batches, which basically makes it confined to batch size and dependent on batch statistics, a characteristic that makes MDN operations suboptimal for small batch sizes and unusable for many novel architectures. So given this method that we published in CVPR 2021, we extended it to another publication in MICAI 2022. We presented it a couple of months ago in MICAI to overcome these limitations, we proposed a penalty approach to MDN, which turns the beta coefficients to network trainable parameters. They can be optimized with other components of a network. So we tested PMDN and on the same data set from 3 different sites. For each batch size for this MRI experiment that we did, we present the 4-class classification accuracy along with correlation between output logits and metadata variables of age, sex, and site. We included all 3 of them as confounders. We compute the PMDN results to a baseline. We compare the PMDN results to a baseline without normalization, a batch norm model, an adversarial model that I presented earlier, and a model with only MDN. For all batch sizes, PMDN consistently has the highest overall accuracy and low correlation values. This concludes my talk. We learned that accounting for confounders is essential to derive meaningful and reliable findings out of the data. At the end, I'd like to thank all my amazing collaborators and the 2 students who I presented the 2 students working on the works that I presented the results for. And thank you, and thanks to the student institutes for supporting my research. I would be happy to answer any questions.
Thank you for Professor Adeli for his excellent speech. Is somebody has any questions about Professor Adeli?
Yes, so it is me again. Well, thank you, Professor Ehsan, for this solving some of my problems. I would like to know that, I mean, as you talked about the age and the diagnosis and I mean, I have a very similar problem. I'm trying to develop a blood test for autism. So I have started training of my algorithm was done in children between 5 to 12 years old. And now I want to use this test for even younger children. And my test set is between 2 to 5 years. And that is giving me a headache. As I said that, I mean, do you think this age is making a difference?
Absolutely, it does make a difference. And this problem that you're explaining is basically a distribution shift problem, because you are changing the distribution of your testing set compared to the training data, which is itself a very challenging problem. Most of these studies that I showed, they cover, like, for example, the training and testing, they cover similar, for example, for age ranges, but there are like biases in age in the training and testing, but it's not that completely the distribution is different. In your case, it's like a complete separation of 2 to 5 years and then 5 to 12 years. So this is an interesting problem. These methods that I presented, they require some samples from the target age range to be able to model and build those linear models, for example, to be able to see how the differences are like in the data. In your case, again, I think distribution shift is the major factor. Actually, we are extending this MDN and PMDN operation right now as we speak for solving this very problem that you're talking about, distribution shift. But generally, the idea of distribution shift has a very like large literature itself. There is a very good benchmark called WILDS, WILDS, which they have like 10 to 20, I think more than 10 smaller data sets put together that actually resemble the very same problem that you're talking about. And and I think that's a good starting point. And there's every year a workshop in NeurIPS under the same name of distribution shift, held by my colleagues at Stanford, which I think they present very interesting methods that you can definitely make use of. They are mainly focused on the natural language processing applications, but I think you will find the methods very useful and relevant.
So your PMDN wouldn't work?
PMDN, the extension we are working on right now, will work because we are actually working on a paper, on a publication on this very topic, either in MICI or on NeurIPS. This year it will be submitted, but the extension will work. But out of the box, this model, it will not, because you have the two entirely different distributions in the training and testing.
Right. So sorry, could you repeat, what did you say, which of your colleagues, what they're doing? What is the name of you mentioned?
Percy Liang. But if you search for distribution shift workshop NeurIPS, you will find that too.
Oh, distribution
shift.
Right. Shift workshop. Right. Okay. Thank you so much. But so just combining the whole set and then training and testing again, that is not a good idea.
You can combine the whole set, but the problem is that then your model will see the testing data during training. So it's not testing it, right? So you can one solution is to have some data labeled from the testing set, include them in the training so that you can build the distribution. And both of these models, MDN and PMDN, and also this adversarial independent feature learning, in that case will work if you have some labeled data from testing that you include in the training and rebuild your model. Right.
Okay. All right. Thank you so much.
Thank you for the great conversation. Any other questions to Professor Adeli? If there are no questions, let's welcome next keynote speech. Thank you, Dr. Adeli. Thank you again. Thank you. Goodbye.